This is the second lecture, and today we are talking about mechanics of rigid bodies. In the previous lesson, we talked about mechanics of particles, where objects that are very large can be approximated to a point in space, and we can discuss the resulting kinematics and forces acting on those objects. In today's lesson, we are looking at rigid bodies, which are actually consisting of many particles. Now, each particle are separated from each other with a fixed displacement, and these objects cannot be generally treated as point sources. But you must also realize that it is also a matter of perspective. If you are very close to this object, then it cannot be treated as point sources because the distribution of masses has a resulting distribution of weights around it. But as you move further and further away from the object, it can eventually be still treated as a point of source. For example, if this is a rigid body, there's a heavy distribution of masses here and another distribution of masses here. And so if you were a person that is on this section, you will feel the effect of the two forces arising from the two different center of gravities. However, if you are a person that is standing very far away, in this situation, because of the distance of the person to this object, it will still be treated as a point source. However, our examples today are going to involve talking about events that is happening within the rigid body, such as the object rotating or the object moving in space, etc. Let us do a quick survey of what we are going to discuss in this section. First, we will be talking about the kinematics of it, so how this object will move. We will revisit some of the formulas that we have seen in lesson 1. Because they are large objects, we will also be talking about something called moments, as the object might have a turning effect about a certain pivot. So we'll be talking about rotations. We will also be looking at a relationship between linear quantities and angular quantities. So linear quantities are those that are moving in one dimension, and angular quantities are usually when the object is rotating. Because the objects are rotating, we will come up with a further concept called the angular momentum and how this is actually derived from definitions. After looking at some examples, we will also be looking at a comparison between translational motion and rotational motion. Here we will start talking about some of the dynamics concepts, such as the moment of inertia. The concept of Euler's second law will also be derived. For the Physics Olympiad, do take note that we are not generally looking at calculus-based problems, but more of algebraic problems. So although the formulas are rather complex, they can be easily manipulated because most of the objects that we are looking at will be point sources like this, or rather discrete sources like this. It is good to have a motivation for why these formulas are derived, and we'll be making a few comments on them, but we will not be required to derive any specific formulas, but aim to apply them in different contexts. And we will also be talking about a comparison between the linear motion, which you will be familiar with in your O-level physics, with rotational motion, which is necessary for the Olympiad, as well as in your further education post-secondary school, you will also be looking into some of these concepts in rotational motion. We will come up with two conditions for equilibrium. So if an object is not moving, we will agree that there are forces acting on it will be equal and opposite, and there will also be moments whichever acts on it will also be added up to zero. That means the object is not turning as well. We discuss mechanics of rigid bodies. We note that rigid bodies actually consist of a number of different particles, of which the relative displacement of each particle from each other is fixed. So you cannot treat these objects as point sources. We define the angular displacement as change in theta, or commonly known as delta theta, as theta 2 minus theta 1, the final angle minus the initial angle, and we measure this in radians. Now we want to know how fast the object is traveling in that arc length. So this can be given by this formula, where this symbol here is known as omega. The brackets here is commonly used to denote a averaged velocity. So this entire section on your left hand side is omega, which is the average angular velocity, is equal to the change in angle over the change in time. So omega equals to delta theta over delta t, measured in radians per second. When the particle makes a complete circle, delta theta equals to 2 pi. And in fact, in the previous lesson, you knew that this actually leads to finding the circumference of the circle. And for a complete circle, delta t is also equals to capital T, which is your period. Those can be combined to give you this formula: omega equals to 2 pi over t, or omega equals to 2 pi f. Now let us look at one example. We are looking at two rectangular bricks of the same size as placed on each other, and they are resting on a table. Because of this system, we want to prevent them from falling over. So we want to see how far we can push the top brick such that the entire system is still stable and balanced. We want to first realize that there are two pivots, one pivot occurring here and another pivot occurring here. So it is easiest if you actually look at the first brick and find out what are the conditions needed for it to remain stable. And once you fix that condition, we will look at the second brick, which is then lying on top of another pivot. So let us take a look. This is the first pivot, and you can push the first box all the way until the center of gravity is directly above this pivot. That means S over 2 will be here. When the center of gravity is directly above the pivot, the object will remain balanced because there is no clockwise moment about pivot 1. Now we look at the second pivot. Even though the object is balanced and does not tip over pivot 1, taking moments about pivot 2, the top box will actually have a unbalanced clockwise moment, and it will fall over about this point, not at pivot 1, but about pivot 2. So now we must try to push back the entire system of consisting of two boxes back to your left to introduce a balancing anti-clockwise moment. So we can now push the second box inwards by an unknown value y, such that it will introduce a anti-clockwise moment about pivot 2. So we have pivot 1 here, which is already balancing the top box, and there's a clockwise moment that is acting on this direction, and there's an anti-clockwise moment acting on this direction. Let us take a look at the equation. So y multiplied by mg, where m is your mass of each of the boxes, y multiplied by mg is equals to s over 2. Now, because you push the entire system inwards by a value of y, this cg will also be moved inwards by a value s over 2 minus y. And mg is also the mass of this box multiplied by the gravitational field strength. That will give you a value y equals to s over 4. So this movement results in a value s over 4. Now, to find out the actual answer, which is the distance from the edge of the table to the maximum position here, you will then take s minus s over 4, which will give you 3s over 4, which is answer C. Let us now look at rotation with constant angular accelerations. So when there is a change in velocity, because the particle is moving in a circle, while the frequency may be constant, the velocity is actually changing, because velocity is defined as the change in displacement over change in time. So velocity is actually consisting of a magnitude as well as a direction. So even though the angular frequency is constant, the magnitude of the velocity is constant, there is a change in direction, and this direction is towards the center of the rotation. We want to connect linear quantities with angular quantities as well. We agreed the last time that this type of motion is similar to, we call this the linear velocities, and there is analogy from rotational motion to linear motion. When there's an acceleration in a circle, we want to find out the forces acting on it. In this specific case, we are looking at the specific form of the force. Previously, we learned that there is a concept called the centripetal force, and it is given by this formula. This formula tells you that when an object is moving in a circle, there is a force directed towards the center of the rotation by a value mv squared over r. We compare this with Newton's second law for linear motion, F equals to ma, and we can recognize that the acceleration is given by v squared over r, and you can also bring in the angular frequency. Therefore, a is also equals to r omega squared. By now, you should realize that most of these physics problems we are trying to solve for forces, displacements, resulting kinematic equations. So the aim is really to have a standard prescription. You will first find out the forms of the force and then start to equate them together. This example here is a qualitative question. A candle is lighted in a glass jar and it is being swung around in a circle about a position. Which direction will the candle point towards? So we know that anything that is moving in a circle actually has a resultant force acting towards the center. This will also include the air molecules that are around. Because of the motion, the air molecules themselves will be directed towards the center. Now, the burning of a candle is a chemical reaction with the air molecules. So we will expect that the flame will also be pointing inwards towards point O. Let us look at a short video clip on this.
This is a demonstration of circular motion. Here we have two candles that are lit and they are inside of a hurricane lantern. I'm going to give the hurricane lantern a little spin and we want to look at the flames on the candles. So we'll spin this. And we try to see that the flames bend in toward the center.
Now let us look at rotational quantities such as angular momentum. Previously, we defined a quantity called the linear momentum, P equals to mv, where P is your linear momentum, m is your mass, and v is your velocity. We can also define an angular momentum, which is a rotational analogy to linear momentum. So L, which is the symbol for angular velocity, is P. We call this as a cross product. So L equals to P cross R. Now P equals to mv. So L, the angular momentum, is mv cross R. This symbol might be new to you. Just take note that it is a multiplication. But the purpose of us introducing cross product is to show you that the direction is in the third axis. For example, if your V is in your x-axis and R is in your y-axis, the resulting angular momentum will be in the z-axis. That is what is meant by this cross product. It is a concept that in spinning objects, this concept angular momentum is conserved. So for example, if you have seen television where a ballet dancer is spinning, when her outstretched arms comes closer to her body, the angular momentum must be conserved. Because her outstretched arms have come closer inwards, r, the radius, has decreased. If r decreases, the linear velocity v must increase, and that is why you see her spinning faster and faster. Let us look at another example on gears. We have three gears that are aligned side by side such that gear A causes gear B to rotate and gear B actually causes gear C to rotate. They have different quantities of the amount of teeth, the amount of angular speed, as well as the radius. We want to know how many teeth does gear B have. So for this kind of very wordy question, it is very often useful for you to actually draw a diagram and put down all the information that you already have, like this. So we know that gear A has 40 teeth and rotates with 50 revolutions per second. Gear B, we are trying to find out the amount of teeth, but it has a radius that is 20 over 100 of the radius of gear C. And gear C is related back to gear A because of the amount of revolutions per second. There is an additional formula we are bringing in here. This might be quite new to the students, but it tells us that the diameter of the two gears are related to the number of teeth each of them has. Now, let us look at how to solve this question. We note that for different gears having different radius, their rotational speeds may be different or their angular frequencies may be different. But at the point of contact, the linear velocity is the same. So when you have, example, these kind of objects, gear A may rotate much more slowly than gear B. But at the point of contact here, they both will have the same linear velocity because they will not have any slipping. They are moving smoothly together with all the teeth connecting with each other. So we know that VA equals to VB. And we also know that V equals to R omega. So let us try to relate using these quantities. We first relate gear B to gear C by noting that the radius B multiplied by omega B equals to RC times omega C. And plugging in the known values, we note that omega B equals to 2 times of omega A. Now we go back to gear A and gear B. Again, we know that the linear velocity at the point of contact is the same. So Ra omega A equals to Rb omega B. We do a division to get Ra over Rb equals to omega B over omega A. We have already established that omega B equals to 2 times of omega A. We plug that into this formula to realize radius of A over radius of B is 2. This tells us a relation between the two radius. That original formula that you saw just now connects the diameter of A over diameter of B to the number of teeth on A and number of teeth on B. Noting that diameter is just 2 times of radius, which can then be cancelled out, you can plug that into this formula and then realize that the number of teeth that B has is 20, which is answer B. Let us look at another example. In this diagram shows a pendulum that is swinging freely. However, there is a peg that is placed at this position, which means that at some point, the pendulum will hit upon this peg and this point P becomes a new position for the oscillations to occur. You want to find out the period of the pendulum. This is rather easy if you remember from your classwork that there is a relation that says the pendulum has a period T which is given by 2 pi square root L over G for a normal pendulum that we encounter in our classroom setting. In this situation, we are going to use this equation as well. So now we want to find out the time taken for the pendulum to go from the rightmost position to the leftmost position. This is actually still considered half of a period, not the full period yet. So we add them up like this. After some manipulations, we get certain values and we'll multiply by 2 because remember from your classroom learning that a pendulum's period is defined as the time taken for one complete oscillation. That gives you option D as your answer. Let us look at another example. A hollow triangular holder of mass M, capital M, is placed on a table. There's a ball with small m mass attached to its interior using 2 springs. They are placed on a table and the spring is then disrupted such that the ball starts to vibrate up and down. At the point when the normal contact force is 0, we want to find out what is the acceleration of this ball. Let's take a look at the total downward forces. The total downward force will be equal to the contact force. Now, downward force is actually due to the mass of the holder itself as well as the mass of the ball itself. So we have the force due to the holder and the force due to the ball. This contact force will become 0 when the ball is actually moving upwards and the top spring actually pulls up this ball, reducing the so-called pressure on the table downwards. So when the ball is moving upwards, the contact force will start to decrease because not much force is being applied to the table. And at some point, the contact force will go to 0. So we want to find out what is the acceleration. So the force of the holder and the force of the ball will be acting in the downward direction, and the resultant force on the spring will be acting in the upward direction. So we can put it as mg plus mg equals to ma. Take note, this a is no longer considered as g. It is a resultant acceleration because in this particular case, this is not an example of free body diagrams. Free body diagrams, in your previous lesson, you learned that the object is only the gravitational force is acting on the object. But in this situation, there is also the spring that is pulling it using elastic forces. So the overall expression will look like A equals to capital M plus M over M times G, which is option B. Now let us look at dynamics, which is another way of saying the forces acting on these rotating objects. But before that, we want to remind ourselves that there is translational motion, which is what we learned in our previous lessons. There is rotational motion about a certain axis, and you can also have translation and rotation together as well. But we are really looking at rotation in this session. We have this equation called Euler's second law, which is actually motivated by Newton's second law, F equals to ma. Euler, what he did is actually to consider F equals to ma for the linear case and then apply it to a situation where the object is rotating. And so this is what we have. Instead of linear forces, we can now look at something called moments. Moments are turning effects about a fixed position. And instead of momentum for linear cases, we will look at angular momentum L. So the sum of all the moments, so sigma here actually is a notation for summation. We add them up. So the sum of all the moments is equals to dl by dt. The change in angular momentum over change in time. But we have already known that L equals to mv cross r, or we can keep it simply, L equals to mbr. And the total effective moment can be called torque, which is basically mv times r over t. This is a Greek letter that we call tau, pronounced as, so tau is pronounced as and what we have done here is we have arranged the variable such that tau equals to mr squared bracket omega over t. Let us look at this specific cofactor here, mr squared. We will define a new variable I equals to mr squared, where I is now going to be known as something called the moment of inertia. And omega over t is nothing but our angular acceleration. So you must realize that tau equals to mr squared multiplied by omega over t can be rewritten as tau equals to I alpha. Tau is the rotational equivalent for your force. I is the rotational equivalent for your mass. And alpha is simply the rotational equivalent for your acceleration. So what does this mean? In particular, of interest is this mr squared quantity, or the moment of inertia. In your physics class, you have learned a larger mass is more difficult to push it compared to a mass which is smaller, because mass is related to a concept called inertia, the reluctance for it to start moving if it is at rest, or if it is already moving, to cause it to change its direction or change its speed. So the moment of inertia here is also a concept that is its resistance to actually start rolling across a floor. So if it is very large, the moment of inertia, it tells us that it is more difficult for this object to start rotating about a defined axis if it is originally at rest. Luckily for us, for our physics Olympiad, most of our questions for this moment of inertia will be discrete point objects. So we can simply add them up like this. So the moment of inertia for a collection of objects is simply the sum of each of their moment of inertias. So mr squared for one object, if you have two of them, you'll find out mr squared for each of them and simply add them up. Let us take a look at some examples. In this case, you have m1 at a position x1 away from a center, m2 at a position x2 away from the center, and m3 at a position x3 away from the center. We can simply find out the total moment of inertia by adding them up. At this point, we also want to make a quick comment. Let us calculate the moment of inertia for each of them individually and do a comparison. For the 1 kg object, for a 1 kg object, 1 meters away, you realize that the moment of inertia is 1 kg meter squared. If your mass increase but your radius remains the same, your moment of inertia will also increase, which must relate to your direct experience because a bigger object, it is more difficult to rotate it. Similarly, if you can try this on your own, if your mass is fixed 1 kg, let m1 be 1 kg and let m2 be 1 kg as well. So the mass is the same. But m2 is further away, let's say 2 meters. Your moment of inertia will increase for the object that is further away from the center of rotation than the object that is closer to the center of rotation. Example, you can compare this one. 1 kg, 1 meters away, 1 kg, 2 meters away. And you realize that the moment of inertia is greater for the object that is further away. And in fact, it is greater than an object that might be massive but closer to the center of the rotation of the axis. So take note, there is a concept now that we are introducing that says even objects that are about to rotate, there is a form of inertia, which we call it the moment of inertia, that is causing it to have reluctance to roll over. Let us look at an example here. This example is easy if you look at it from an intuitive point of view rather than actually solving it by complex methods. There are 4 cylinders here. Each of them have the same mass m and certain length L and radius. However, object A is solid outside and hollow inside. Object B is actually solid inside and hollow outside except for these two supporting structures. Object C is a non-uniform object where all the white section here is hollow, but there's a solid section close to the edge. And object D is a completely solid cylinder. And they are now rolled over a slope. Which cylinder will arrive at the bottom of the slope first? Again, same thing, we will try to solve it by intuitive reasoning because you have quite a few MCQ questions to be solved within a certain amount of time. So by intuitive reasoning, rather than to perform explicit integration, what we will do is to look at the moment of inertia I equals to mr squared. Any massive object will have a very large m, so that immediately eliminates option D from your choices. You can now look at options A, B, and C. Option A tells us that the mass is further away from the center of rotation, and we have established that if the mass is further away compared to the mass being in the center, option A will also have a greater moment of inertia, which means it is ruled out as well. Option B and C may look very close, but look carefully. Here, the effective mass distribution away from the center is actually very near. Whereas in option C, the masses are all very far apart, causing it to have a greater moment of inertia. So option B is the correct solution. You might have some experience with this if you played with hoops which might be damaged and then they start to wobble around. They will actually take a longer time than hoops that are perfectly circular. You can also try a simple experiment at home using a blue tack as well as a coin and place the blue tack at the edge as well as at the center and see the amount of time it takes for it to roll down a straight object like a ruler. There is some background provided here. We will not focus too much on this for the Physics Olympiad, but if you are taking an engineering course in your polytechnics or physics at your JCs, you will come across this again. The general form of moment of inertia is again I equals to the integral of r squared dm, because in a general situation, the mass distribution may not be symmetrical. And based on the type of object that you have, you will then put in the form for mass and then perform the integral explicitly. However, for our physics Olympiad, we will keep it to very symmetrical objects, of which if you do need the form of the moment of inertia, generally it will be provided for you. So if it's a very complex object in the physics Olympiad, the form will be provided for you. But most of the time, we are looking at discrete objects, which makes it easy for us to use the symmetry involved to solve for them. Here we have a comparison of the linear motion and the rotational motion analogies. So this gives us a rough example. Like position, instead of talking about position, we talk about the angular position. Instead of talking about linear velocities, we talk about angular velocities. And we also have accelerations, and we have variations of the equations of motion. Instead of talking about mass, we'll talk about the moment of inertia. And there's an associated Newton's second law for rotational motion as well. We talk about angular momentum instead of linear momentum. And we also have kinetic energy, etc. Let us look at another example. A man stands at the center of a turntable, holding his arms extended horizontally with two masses on each hand. So you already can see that the fact that he has discrete objects in each of his hand, you can simply add them up without doing complex integrals. He is then set in motion with a certain angular velocity. The moment of inertia for the man is about 6 kilogram meter squared, and his arms length are given as well. And now we want to see what is his angular speed if he drops his arms to the side. First, we note that, as we mentioned before, the moment of inertia is luckily simply an addition of individual discrete moment of inertias. So this is the moment of inertia for the man. This is the moment of inertia for the weights, of which you know that m is 5 and r is given as the distance 1 meters from the center. So the initial moment of inertia is given, the final moment of inertia is given. We also know that the angular momentum is conserved once he starts to spin. It is a play between two quantities. L equals to m v cross r. M is a constant because he didn't drop the mass. He just held on to it and then he moved it closer to his sides. So if your radius actually decreases, your velocity will start to increase. But you also know that the V is equals to R omega. And the question is then asking for this final angular frequency. Revolutions per second. Let us look at another example. 4 samples of a mixture are placed in this centrifuge. Each of them weighs 12 grams and the distance is given. The motor itself gives a constant torque of 0.25 Newton meters, and we are also given the moment of inertia of the empty rotor. So how long will it take for the rotor to accelerate, assuming from rest to a final operating state of 18,000 rotations per minute? So take note, this is an analogy to this is an analogy to talk about similar to acceleration. Let us take a look. So we know that the torque is actually the moment of inertia multiplied by acceleration. And we also know that this acceleration is similar to acceleration, which is defined as final velocity minus initial velocity over time taken. We are going to use this as an analogy for our revolutions per minute. So we start off by this formula. The torque equals to moment of inertia multiplied by the angular acceleration. So tau equals to I times alpha. The torque is given as 0.25. The moment of inertia of the empty rotor and the samples can be simply added up as under I. The revolutions is kept under alpha. Just take note that these revolutions must be converted to an angular value. So we multiply by 2 pi to get the angles out in radians. The 60 comes about because we want it to be by the seconds, not by minutes. After some explicit calculation, you'll get t equals to 456, which is option B. Let us look at another example. A drum has a radius of 0.4 meters and a moment of inertia of 4.5 kilogram meter squared. There's a frictional torque on the drum axle, 3 newtons meters, and a 15 meters length of rope is also wound around the rim. It's actually at rest initially. A constant force is applied to the free end of the rope until the rope is completely unwound and it starts to slip off. And at that time, the angular velocity is 13 radians per second. So the drum decelerates and comes to a halt. The constant applied force to the rope is to be determined. So this diagram actually looks like this. There's a constant force, this is the rope itself, and it's being pulled. The overall torque is the applied torque 0.40 multiplied by F, which is the force. So radius multiplied by force gives you a moment here minus the frictional torque, which will give you then the resultant torque. The resultant torque actually causes a moment of inertia multiplied by the final resulting accelerations. Then we substitute in the values. I is 4.5, which is the moment of inertia of the drum, multiplied by R squared, which is 0.4 squared, multiplied by 13, which is the angular velocity here. From here, you discover that F equals to 33 newtons, which is option E. So take note, it is easiest to solve these kind of questions if you keep in mind that the rotational motion has an analogy in the linear motion. This was nothing but the resulting unbalanced moment. In linear motion, we have resultant force. This moment of inertia is analogy to mass in Newton's laws. And alpha is similar to acceleration. So everything that has a linear mechanics will have its rotational analogy. So we also have equations that relate to kinetic energy for rotating objects. We simply substitute V equals to R omega into this equation and we get mr squared omega squared, and then we express this in terms of the moment of inertia. The last section here we are talking about is equilibrium. An object is in equilibrium only when two conditions are applied. One is all the forces acting on it are balanced, which means the object is not moving in a translational way. Secondly, all the moments that is acting on the object must also be equals to zero, which means about any point on the object, there is no unbalanced moment which is causing the object to start to rotate. So an object is in equilibrium if it is not moving and it is not rotating. So this concludes the end of session 2. Please try the questions at the bottom of these notes.